Okay, so I was waiting for more people. Is this recording? Let me check. Okay, it's recording. I was delaying class to see if more people would show up, but we're 3 strong today. So if you're listening online, welcome. Wish you could be here. Okay, so I'm going to tie some loose ends up with VSEPR, then I'm going to go into molecular orbital theory, which is the real deal. So this is what teaching this stuff's hard, because this theory that I'm talking about now, it's not the most correct theory, but there are some things that work with it. So this is valence bond theory, and the idea is that the way that chemical bonds form is an overlapping of the electron cloud. And this, what I'm going to talk about, is absolutely true. That's not how bonding forms. Bonding forms by molecular orbital theory, which we'll talk later. But if you look at this diagram is absolutely true. The y-axis is energy. The x-axis is the internuclear distance. So if you look at 2 hydrogen atoms, so here's 2 hydrogen atoms really far away, and as the hydrogen atoms approach each other, they start to bond. And also as they bond, the energy level goes down. So they start to bond, and I'm using the altitude being the energy level. And then they have this sweet spot here where they're like the perfect distance apart. But if they get closer, then the energy goes back up and actually becomes repulsive. So the reason for the energy going up is the nuclei. The nuclei are both positive, and so when the positive nuclei come close to each other, the potential energy increases. But then there's a certain point where the potential energy decreases, and this minimum, this is known as a bond length. So that's where it tends to go. And we talked about this before, this is kind of like your basic flirting principles. So like remember I talked about that with flirting, like one of the easiest ways to flirt with someone is to get close to someone. So when you're far away, if you want to meet someone, you're like, oh wow, I like you. I'm going to stand over here, right? So being far away from someone is not necessarily a good thing, unless you look better that way, I guess. But then, so it depends on the person. Your strategy, different strategy. But then there's a certain like perfect distance. You're like, oh, I'm comfortable and I can look at you and we can talk. Then, of course, if you start getting closer to someone, there comes a point in time you're like, oh, you're a little close. Like, now you're really close. Now I'm repulsed. Same thing with atoms. So there's a good distance here. They can share electron density. Too close, now the nuclei start to repel each other, and it's better if they just keep their distance from each other. So bonding is okay, but too close of a bonding is not okay. And with this theory, so if you look at a molecule like hydrogen sulfide H2S, the bond angle in that is a tetrahedral, so it's 109.5. But if you say, okay, well, a sulfur atom's got p orbitals, a hydrogen atom has an s orbital, and the p orbitals are 90 degrees from each other. So the bond angle in hydrogen sulfide should be 90 degrees perpendicular, but it ends up being 109.5. How does this happen? Well, how this happens is, and also same thing with, here would be for methane, so carbon has a p orbital, you'd think that there would be a 90 degree angle in that. But what happens is that the s orbitals and the p orbitals, they hybridize. So they hybridize to form, so these 4 atomic orbitals, the 1, 2, 3 p's, so 3 2p orbitals and 1 2s orbital, hybridize to form 4 sp3 hybridized orbitals. And the idea with that is these hybridized orbitals then form the tetrahedral electronic geometry. And if you remember 2 lectures ago, I mentioned this, that the hybridization for tetrahedral electronic geometry, solve these electronic geometry, hybridization is sp3. So this is coming back to back in the picture. And so then here would be the overlap theory with the with the methane molecule. So the tetrahedral overlap there of the 4 sp3 hybridized orbitals. So what about planar? Planar is sp2 hybridized, and it forms a shape like this. So there's an s orbital and 2 p's, and then it forms that clover leaf. Well, each one is a big lobe and a small lobe, and then all three overlapping has this kind of 3-leaf clover thing all in the plane. So, but then how do you deal with double bonds? So this is, up there is, that's formaldehyde, the C2H, or I'm sorry, H2CO, so C double bond O. How does double bond work? So here's carbon with the sp2 hybridized orbital, and so there's a hydrogen here, and then there's an overlap here, but now there's an open p orbital. So, and then the open p orbital can give the second bond, the pi bond. So let me explain this. So if you look at my heart and my fist, so if there's a single bond, every single bond is what's known as a sigma bond. So a sigma bond goes parallel to the internuclear axis. So, and this is lowercase sigma. So one atom here, the internuclear axis is my arm, right? So it bonds along the line between the two nuclei. A pi bond, so if this is the sigma bond, the pi bond is going to be here. So above and below the axis. It can also be here. So it can be above and below or flipped 90 degrees. So because there's 3 dimensions. So and every single bond is a sigma bond. A double bond is a sigma bond and 1 pi bond. A triple bond is a sigma bond and 2 pi bonds, which we'll cover later. So, is this making sense? No, not really? Are you getting stuck on something, or you just needed more time to process? Oh, there'll be lots of, yeah, there'll be pictures. So, okay, so a couple of things. So also with bonding, if you have a single bond only, a sigma bond, and you have a group on it, a sigma bond, it has free rotation. It's easy to move. So it'll just fly around however it wants. If you have a double bond though, so it has the additional bond here, it can't rotate. So if this bond rotates like this, or if it rotates 90 degrees, it has to break this overlap. So the pi bond is fixed here. So if it rotates, it has to break the double bond, or at least the second bond, not the sigma bond, but the pi bond, the second bond. So because of that, it's really hard to break. It's not so easy. You can break a double bond, but it's harder to break that to freely rotate. And an example of that here. So if you see this molecule, this is 1,2-dichloroethene, all single bonds, and this molecule can freely rotate. The chlorine can go wherever it wants. But if you have a double bond here, now you have, remember we talked about cis and trans? So this one here, this is cis 1,2-dichloroethene, and this is trans. So cis is same side, trans is opposite side. So these are 2 separate molecules. So, and this one is polar, this one is nonpolar. So if you want, you can take these mixtures and you can start pouring them and then put a magnet and This one will go towards the magnet, and this one won't. So you can separate it out with a magnet if you wanted to, if you have a mixture of it. So, but in order to go from cis to trans or trans to cis, the double bond has to be broken, or at least one of the bonds, not both bonds, but one of the bonds has to break. So how do you, what's that? How do you break a double bond? Well, you can do it with energy, temperature, you can raise it up. But another way you could break bonds is with a photon. So a photon can provide energy to do that. So, and that is in part how our eyes work. So there's this molecule. So 1,1-cis retinal, so retina in our eyes. So this molecule exists in our eyes. And if a photon hits a rod or a cone, it can switch from cis to trans. And that, among other things, is what causes the signal in our eyes to work. So there's other things. It's much more complicated than this. This is attached to a protein called rhodopsin, for instance, and there are different gene mutations with the protein rhodopsin. So some people see colors differently, and some people have things missing, which we also refer to as color blindness. Some people are superior. They're known as tetrachromes. But this is in part the cis-trans switching using the photon of light is how, in part, how we have photosensitive cells in our eyes. So, are you still stuck on the free rotation, or? Free rotation, sigma bonds have free rotation, pi bonds do not. Okay. So here is your summary. Actually, no, I should go back. Not listed here is the SP, so linear. So, okay, back up. Tetrahedral is sp3, planar is sp2, and linear is sp. So, an s and a p orbital will form the two lobes there, like that.
And hybridization starts at sp3.
Well, either way, it depends on how you want to build it up. You can, if it's linear, it's sp. That just means an s orbital and a p orbital form a hybrid orbital. It's actually not real. So, but
Do you need to worry about hybridization?
Organic chemistry uses this theory a lot. Are you going to take organic chemistry?
Yeah.
Then you don't have to worry about it.
Cool.
Although there might be, I think there's some questions on the final with that, so I can show you. I'll direct you exactly what the questions are, or the type in a second. Yeah. So I guess you could argue, I would argue it starts with SP, and then for planar it's SP2, tetrahedral SP3, bipyramidal SP3D, octahedral SP3D2. So, and that also, if you remember the charts here, I added that to this chart here, the hybridization. Okay. And let's talk about the bonding scheme in ethylene. Or it says ethene, but ethylene is the common name, like dihydrogen monoxide versus water. Water is the common name, so ethylene is the common name for this. Ethylene, ethylene is something that's known as autocatalytic. So have you heard the phrase, and what this molecule does, ethylene, it causes fruit to ripen. You ever heard the thing, a bad apple can spoil the whole bunch? Right? So if you notice that rotten fruit makes fruit ripen or rot faster, and it's also a process that's referred to as autocatalytic because ripening fruit causes ethylene, which causes fruit to ripen faster, which causes more ethylene, which makes it ripen faster. So fruit can rot really quickly if there's a big source of ethylene there. And at least I've noticed this. Have you ever, when fruit ripens, or I should say when it rots, anything, when it rots, at least plant matter, it has a similar smell. I bought this big bag of carrots one time from Costco, and I never got to finish it. I finally opened it up, and then I smelled the ethylene, but it smelled kind of like bananas. I usually think of bananas when I smell the ethylene smell, but it didn't. I mean, banana has another flavor to it. I mean, it's more than just the ethylene, but there's I mean, at least as fruit is ripening, you're like, well, that kind of smells like rotten fruit. You're like, oh, that's guava. You know, you have to like oh, ripened. It's like rotten fruit, and you're like, oh, guava or oh, banana. You know, kind of thing. But you can kind of tell that something has overripened. What you're smelling is ethylene. But to me, the closest smell is banana. To me, at least, anyways, to that. I mean, I used to live on Oahu for 11 years. Anyone ever been to the Health Bar on Oahu? No, you haven't. It's this restaurant right by Kapiolani Community College, and it's called the Health Bar. That's when back like acai bowls were really popular. Like they opened up, and but they like to make banana bread, so they always have these bananas in the front of their place. And if you walk in there, it's like a smack across the face. The ethylene smell, it just hits you. And the other thing is sometimes fruit is treated with ethylene. They tend not to do that here in Hawaii. They did that more when I lived in Ohio. Like if you ever bought a banana though, and then it's like yellow on the outside, and you tear it open, it's like raw in the middle. If that happens to you, it's because they treat the fruit with ethylene to make it look better. And they do that with meat too. They don't use ethylene for meat. They use carbon monoxide. So poke and meat, we actually treat it with carbon monoxide to make it look better, so it doesn't look brown or something. Or like because some fish, raw fish, can look brownish colored, and people don't like that. It turns a pinker color with carbon monoxide. So all the tricks they do. Sometimes they put dye in fish as well. Like sometimes salmon is dyed. What can I say? You're being fooled. But okay, well here's ethylene, and ethylene. So the carbon here has three things. So it has a hydrogen, and a carbon. So that's three things. That's planar, which planar geometry means sp2 hybridization. So there's an sp orbital here, here, and here, and then there's a sigma bond between the two sp orbitals of the carbon. Sigma bond here, and then there's a p orbital. So that means so if my heart is the carbon, you have two hydrogens here. So there's an sp orbital, sp2, sp2, sp2 here, and hydrogens here. And then there's another carbon here, but then there's open p orbitals, and then it can bond alongside here. So there's a sigma bond and a pi bond here, sigma bond here, sigma bond here. So this molecule has 5 sigma bonds, sigma bond here, sigma bond here, sigma bond here, sigma bond here, and then a sigma bond between the two carbons. And then the double bond gives another pi bond. So 5 sigma, 1 pi. And a shortcut, a single bond is a sigma bond, a double bond is 1 sigma, 1 pi, a triple bond is 1 sigma and 2 pi. So you guys are write that down, okay. And again, here is the hybridization scheme. So if it's in electronic geometry, linear SP, planar SP2, tetrahedral SP3, bipyramidal SP3D, octahedral SP3D2. So what is the hybridization of sulfur in sulfur hexafluoride, SF6? So how many things are on sulfur? There are 6, which means what type of geometry? That means octahedral geometry. 6 is octahedral, and then octahedral means what type of bonding? sp3d2. So it's sp3d2. And you will be provided. I need to look at the test again to see if there's, if this type of test question is there. I'm pretty sure there is on the test, but you'll be provided that. So I'll let you know if this is false. But I think the way the test works is you're given a molecule like this.
Well,
Actually, maybe I should do it. Let me make it smaller. So what's the hybridization in carbon number 1? It's a linear geometry, so that means SP.
and it's linear because
There's two things.
there's two.
Yeah. Has two groups, both bonding. Doesn't matter if it's single or triple bond. It's just two groups. Carbon number 2 has three things, all bonding. So that means SP, 2. And carbon number 3 has four things, all bonding, sp3. Make sense?
One was SP.
One is sp. Okay, I'll write it in black. This is that's too small. This is sp. This is sp2. This is sp3. And that's because two bonding groups. So this one is sp because there's two groups. This one is sp2 because there's three groups. And planar geometry means sp2, linear means sp, and three things here means four things, four bonds, four things, which means tetrahedral, or which also is sp3. So we'll go over that too when we talk more about reviewing. You know, I do post the videos and the lectures and the things online. Yeah, but you're writing it down. That's fine. Okay. A single bond is sigma bond. A double bond is 1 sigma, 1 pi. A triple bond is 1 sigma, 2 pi. Nitrogen has how many pi bonds?
Oh,
So if everyone, are you gonna piece me two? Everyone's giving me two. It's two.
sweet.
It's this one because it's a triple bond. A triple bond means 1 sigma and 2 pi.
We're gonna have to figure out how the elements bond together. So nitrogen with its three bonds. We're gonna have to figure out like if two sulfurs are bonding or two carbons are bonding.
it would more or less be given to you in that regards, I guess. And so a question like that you can always ask me if it's not clear. Okay, so here is diatomic nitrogen, and showing you it's going to have an sp hybridization. There's a sigma bond here, and then so nitrogen. So it's going to have a sigma bond alongside that. There's going to be a pi bond here, and a pi bond here. This actually is not how it works. So if you would think, if you look at this picture, has anyone ever been to an artisan soap shop before and seen those long pieces of blocks of soap, and then they have different colors and shapes, and you can cut them? You have seen that? Yeah. Okay. So when I look at this, I think of like a clover leaf. Can you imagine like a long clover leaf shaped piece of soap? You know what I'm talking about? Like you have a clover leaf on it, and then you can like slice it into clover leaf shaped soaps. That's what this kind of looks like. How nitrogen really looks like, it's more like a football. So there is not this division between the orbitals. Actually, what happens is that it forms more of a cylinder, but it's kind of a hump in the middle. So there's the nuclei, and there's more overlap here than it is less on the edges. So it's actually more like a football. So that's how nitrogen really is shaped, like a football, or like a Tylenol, if you will, or like the body of an airplane kind of shape. You know, it's not going to be a clover leaf, or a four-leaf clover. It's not going to be a four-leaf clover. So, but that's what would be predicted by molecular orbital theory. So here's the shape. It would look kind of like that one. That's what nitrogen really looks like, is the bottom one there, the blue thing. Okay, so we're finally getting to the real thing. Okay, so we're at the, have you had this experience as a student? I guess you kind of still pretty early in your career. I always hated it when I took a class and then the teacher said, this is the way it is. The next class says, oh, by the way, that's wrong. This is how it really is. Oh, by the way, that one's wrong. That's how it really is. And then you get to, if you eventually get to grad school, sometimes they say, well, you know, we really don't know what we're doing. Some of it's true, we don't know what we're doing. Some of it's true that we really know what we're doing. Some of the things with like the human body, we have no idea what we're doing, right? So I mean, that's why when people take drugs, it's a crapshoot. Some people respond to it properly, some people don't. It's just because we don't really understand what's going on. But we have like experimental data suggesting that if people are depressed, if you give them these drugs, they feel better, kind of thing. But it doesn't always work. Or if you have cancer, this drug sometimes works. Doesn't work for all cancers, doesn't work for all people, then we try this one, then we try this one. It's like, I mean, you're essentially going through like an experimentation. We're getting better at it though. I mean, in the simplest ways, we've tied the genetic code to drugs. So my parents, they're like, my mother has dementia, my father has cancer, and they've taken their genetic code and they've treated them based off of their genetics. So, I mean, so they're getting better, but we're still far away. And some things we know really well. I mean, salt is sodium chloride. That's pretty well known and understood. But like how electrons bond in some things, there's some things that we don't know. But we do know this, and this is the truth. You find the truth. The reason why where bonds come from is that the electronic and magnetic field of an electron forms new energy levels. And if those energy levels form and then the atoms and their arrangement and the energy level is lower in energy than them being apart, then they bond. If it's not the same energy level, if it's higher energy level, then the bonding doesn't form. And we're also, the recent research also suggests it's the environment in which the molecule forms. I think I mentioned this class before, but this has an application for astrobiology. So if life can form outside of the Earth. So there are certain molecules that just cannot form in space. So there has to be other matter around it. So simple molecules, things like alcohol. So alcohols, like at least a small ethyl alcohol and methanol, those can form. Methanol is CH3OH. Ethyl alcohol, CH3CH2OH. Those are small molecules. But a molecule like cholesterol, that's not going to form in space. So maybe an amino acid can form in space. Actually, I think they have seen amino acids in space, but I mean, a huge structured protein, that's not going to form in space. That cannot randomly form. So you have to have a liquid environment specifically for that to happen. So, and so that tells us about life as we know it, where it can and can't be, and where it could originate from. So, okay, but anyways, we're going back and talking about molecular orbital theory, and this is an approximation called the linear combination of atomic orbitals, LCAO, linear combination of atomic orbitals. And I don't know why my poltergeist came through and deleted this stuff. Linear combination of atomic orbitals. Okay. And so let's go back to hydrogen. And you have two hydrogen atoms approaching each other. And when the hydrogen atoms get close, what happens is the energy levels split. So let me try and mime some of this for you. I'm talking, it's not miming. I guess I'm visually demonstrating. So imagine the altitude being the energy level. So here are two atomic orbitals at this energy levels. As the atoms approach each other, what happens is they split. So these atomic orbitals go away, and then two molecular orbitals form. So they're at this level. One goes below, one goes above. And for hydrogen, it's actually completely symmetric. So the amount that this goes down is the same amount that this goes up. That doesn't work for every single case. So this works for homonuclear diatomics. So homo means same, and so homonuclear, same nucleus, diatomic, two atoms. So if you have homonuclear triatomic and beyond, it doesn't work that way. If you have heteronuclear, even two, it doesn't work that way. Hetero means different, so different atoms. But homonuclear, but so for this class, you only have to worry about homonuclear diatomics that are only have a sigma scheme. So we'll talk about pi schemes next. So the noon class, we didn't get to the pi schemes yet, so we'll cover it on Monday. So, but then, so the molecular orbitals form, and you have the constructively interfering, so this is a bonding orbital, and then the destructive interference, also known as the anti-binding orbital. So here, this is kind of like if you have two people, you can either love each other and hug each other, like they do in the bonding orbital, or you can be angry and point away from each other. It's like this is the anti-bonding is kind of the pouty state, and this is the loving state. So, and so a couple things to note with this. I'll show you that. There's the constructive interference and destructive interference. If you ever, this is outside of this class, outside of this test, but if you look at these molecules through an inversion center and you compare pieces alongside, I should use a different color. You see yellow? Yeah, you can see yellow. If you look at these two through inversion, so this one here, meaning if you go through the center, if you invert it through the center, this molecule is the same going through, at least the sign of the wave function. Up here, the sign is opposite. So if the sign is asymmetric, so not symmetric, that is known as ungerade. That's German for not symmetric. And then if it's symmetric, it's known as gerade. So again, this is German. I don't know German. German, you used to have to learn German if you took chemistry. But now most of the science is done in English now. So English is, so we're lucky, at least we as Americans are lucky, because English is now the international language. So yeah, I'm gonna hate it if it ends up being Chinese. So, but so right now English is the international language. It's the international language at airports. It's the international language for science. It used to be German. I don't know about airports, but German used to be the language of science. So, what's that?
Makes sense.
Yeah. So, but after World War II, guess who won? And but it's okay. So, and the symbol sigma. So it's a sigma bond. This without a star, it means bonding. The star means anti-bonding. And the G or the U, that's beyond this course, but this is important with spectroscopy. This changes the way that the molecule reacts to light. So in the future, you can, if you want to study more about this, you'll learn that the symmetry or lack thereof is important for the way that the molecule interacts with light, and thus spectroscopy. Okay. And then bond order. So bond order, BO in chemistry class is the number of bonding electrons minus the number of bonding electrons, minus the number of anti-bonding electrons divided by 2. So for hydrogen, the hydrogen atom, the bond order for hydrogen, this is 2 bonding. So, okay, let me zoom in on this chart. So here's hydrogen. This is what I said. And a misconception about these s orbitals, these go away. So if you have 2 hydrogen atoms, they're s orbitals, they disappear, and then they turn into molecular orbitals. So the electronic and magnetic field of the electrons and the nuclei, they go away from s orbitals to molecular orbitals. And now each hydrogen has 1 electron. So then this lower energy level right here, 2 electrons go into it. So 1 electron, 2 electrons into this lower energy level. And this sigma, that's a bonding orbital. So the bond order, there's 2 bonding minus 0 anti-bonding divided by 2. This is a bond order of 1. So now we've predicted that hydrogen is going to have a single bond, you know. And of course, hydrogen has a single bond. We already know that. What about helium? So can helium form a molecule? Why doesn't helium bond with itself? Well, if 2 helium atoms approach each other, what happens is, and this does happen, the helium will approach each other. So 2 heliums come together, and then their atomic orbitals turn into 2 molecular orbitals, and then the electrons populate, but this has a bond order of 0, though, because there's 2 bonding and 2 anti-bonding over 2. This is 0 over 2. So bond order of 0 means it's not going to bond. So diatomic helium does not form. But let's say you have a certain case, somewhere where it's really hot, like the sun. Right? So the sun, you could see, imagine you see some helium ion, so He plus ion. Could this ion then go and react with another helium atom? And in this case, let's look at that. The bond order here is 2 bonding minus 1 anti-bonding. That's the anti-bond. Divided by 2, which is a half. The positive bond order means it's stable. So that means that you would think that there would be He2 plus in the sun. And it turns out that there is. We actually can't see this. And He2 plus is different than helium. So remember when you have the atomic orbitals and now it forms molecular orbitals? So the atomic orbitals go away, and we have molecular orbitals. And we can do spectroscopy on the molecular orbitals. So I know you like astronomy. Like, have you ever wondered how they say these certain things? Like, I like the Titan. I think it's interesting. The Titan, the moon of Saturn. Titan has an atmosphere that's almost entirely nitrogen, but it also has methane, and there's also clouds of ethane, and there's liquid ethane on the surface. So Titan is the only other celestial body other than the Earth that we know of that has liquid, a large amount of liquid on the surface of it. How do we know that? I mean, I haven't been to Titan. No one's been to Titan. Well, we send probes there. So we sent probes to Saturn, and so here's the sun, here's Titan, here's the probe. The sun shines through the atmosphere of Titan, so that way, and nitrogen, so diatomic nitrogen, they don't have atomic orbitals. Diatomic nitrogen now has molecular orbitals. We can see through the spectroscopy the way that the light interacts from the sun with the nitrogen. We know that nitrogen is there. Just like on the surface, if we see the light bouncing off of the lakes, we can tell from the molecular orbital scheme and some other spectroscopy points that it's a liquid. It's a liquid form of ethane, C2H3. So by using spectroscopy and the fact that there's new orbitals from this can tell us the identity of things. So I think it's kind of cool. Okay. Anybody here like Star Trek? I'm the only Star Trek fan, huh? Oh, man. I need more nerds in my class.
You never watched it.
Never watched it? Not even the new movies with the Abrams and all the lens flares? Man. You don't like lens flares? You ever seen Abrams movies? They're all full of lens flares. We're still recording. Oh, shoot. I sometimes play drinking games, and you have to drink at every lens flare.
Well,
You ever do that with movies? Okay. Okay.
not old enough.
Oh, really? Oh,
So,
how old are you?
20.
Okay. Oh, man. I'm feeling old. I'm the big 3'9". But, all right, well, I drank when I was 20. But anyways, okay, well, okay. Now, let's talk about some other atoms, or molecules. So lithium has one valence electron. So two lithium atoms can come together and can form this. So two electrons. The electrons can populate like this. And the bond order is 2 bonding minus 0 antibonding divided by 2. And this is a bond order of 1. So guess what? Dilithium does exist. So I was trying to get the reference to Star Trek. Dilithium is what powers their vessels. So, but in Star Trek, it's a solid. Dilithium would not be a solid. It would only exist in the gas phase. So, and the reason is because lithium metal. So it's liquid. So if lithium's a liquid or a solid, it's going to be a metal. But in the gas phase, it can either be lithium atoms or it could be diatomic lithium. So diatomic lithium can form. What about diberyllium? Beryllium has 4 electrons, so each beryllium atom has 2 electrons. And then it forms 4 electrons like this. And the bond order is 2 bonding minus 2 antibonding divided by 2, which is 0/2, which means it's unstable. So diberyllium doesn't exist. So, but I will talk about this. So which one is the highest bond order? So let me show you this. Here is, well, let me see if you can figure this out. I'm curious. I'll give you a few seconds. Then I'll explain it. The noon class couldn't get this. Your homework today is to go watch Star Trek. Just kidding, of course. So beryllium normally has 4. So I think it's A, I think it's B, and it's C, or D. Okay. So let's start with beryllium. B, this A. For A, it's going to be 2 bonding minus 2 anti-bonding divided by 2. This is 0. For B, so B is going to have 1 less. So that's 2 bonding minus 1 anti-bonding divided by 2. This is a half. C, it's going to be this case where you have 2 bonding, 0 anti-bonding divided by 2, which equals 1. And then D is this last case where you have 1 bonding minus 0 anti-bonding divided by 2, which is 1/2. So you get that? This is, so beryllium plus 3. So beryllium only starts with 4, it means there's 1 electron. So that has a bond order of a half. Beryllium plus 2 has 2 electrons. It's like this. Beryllium plus 3, it's like this with a bond order of a half. And then beryllium 2 has a bond order of 0. Are you following that? Not really?
And so what were we trying to find out?
What has the highest bond order?
Oh. C?
Yep. Yeah. It's this one. Because so I'll start one by one. Okay, so beryllium 2, bond order is 0, right? So it's 2 bonding minus 2 antibonding divided by 2. That's 2 minus 2 is 0 over 2. So, so beryllium plus, this is 2 bonding minus 1 antibonding divided by 2. That's 1/2. Did you get that? You look confused. So this
plus,
is...
So plus 1 will mean that it has 3 electrons.
Yes.
Okay.
There's 1 missing.
Plus 2 is 2.
Plus 2 means 2 electrons are missing, like this. Right, so then in this case, it's this one down here. 2 bonding minus no antibonding divided by 2. So this tells you a little bit more about chemical bonding though. So which makes it difficult to describe chemical bonding because it depends on the circumstances. So in some cases, ripping off electrons can strengthen a bond. And sometimes ripping off electrons will weaken a bond. It just depends. It depends on what the bonding scheme is. Sometimes adding electrons will strengthen a bond. Usually when you add electrons to a bond, it breaks it. And this is how acids and bases work. This is not till next semester, but there's a theory called the Lewis acid and base theory, where Lewis acids are electron acceptors and bases are electron donors. So, for instance, hydrochloric acid, the hydrogen pops off of hydrochloric acid. How that works is water gets close to HCl and the electron cloud of water gets added onto the hydrochloric acid, so the water will donate electron density to HCl, and then that will break the chlorine hydrogen bond, and then that hydrogen will attach itself to water to form H3O+. So that's the Lewis acid and base theory. So that's how, but back of that is, how can water break the bond? Water breaks the bond by adding electron density to hydrochloric acid, which then will rip off the hydrogen. So and it works out because it adds electron density to the antibonding orbital. But that's tricky though, because sometimes adding electron density strengthens a bond. So of course, then adding an electron density to that, then the bond would form between the two molecules. So, but it just depends on the context. So, and the context is the math. So it takes lots of math. Okay, and right now though, when it comes to molecular orbital theory, there are a few more topics I'm going to cover on Monday after Thanksgiving. But for chapter 10, this is it for the final. So if you can do the bond order with a homonuclear diatomic, then you're good. And you'll be given the orbital diagram. So it's a real simple question. There's no heteronuclear, there's no homonuclear above the simple sigma bond. So we can talk about the p orbitals, but the p orbital is going to happen next class. But I might as well end class with a conclusion, though. So here's the sigma bonding scheme for a p orbital. So that's what the bonding orbital and the anti-bonding orbital looks like. For the pi bonds, this one is just the same, just the opposite plane of this, because remember, p orbitals are in one's above and below, the other one's this way. So it's easier to see this way. And there's the bonding. It's kind of like, well, s orbitals are always positive. The p orbitals, there's a positive and negative sign of the wave function. So you have the positive overlap here with the positive and negative sign of the wave function for the bonding orbital, and then you have the opposite for the anti-bonding. But we talked about the inversion through the center. With the sigma bond, the symmetric one was the bonding. For a pi bond, the symmetric is the anti-bonding. So actually, this one is symmetric. So, and the bonding one is asymmetric. It's not symmetric. So that's a switcheroo for that. And I'll get into this more. I mean, even though I'm telling you as a student, this is not on the final, just because you guys want to know what's on the final. Like, what do I need to study, what I don't need to study, and this stuff is pretty complicated. I can understand that you want to be strategic on what you're studying. So I'm telling you this is not on the final, but I'm still going to teach it. So, because it's important for other classes if you take other chemistry classes. This is the molecular orbital diagram for oxygen. So oxygen is predicted to be this way with molecular orbital theory. And notice it has two unpaired electrons. That means it's paramagnetic, which means it responds to a magnetic field. So here, this is the scheme for oxygen using the band overlap theory, and everything's paired up. This would suggest that oxygen does not respond to a magnet. And it turns out that oxygen does respond to a magnet, but this fact here is what made molecular orbital theory valid. So it's kind of like right now string theory versus quantum mechanics in physics in this current and contemporary physics. This was a big deal like in the 70s. The fact that molecular orbital theory turned out to was proven to be correct, and VSEPR was proven wrong. So I guess it wasn't like as big as like Nixon going to China or something like that, or Nixon resigning, but I mean, or the Vietnam War. But it was a scientific news story. But we'll pick up here again, I guess, on Monday. I guess you'll get a little bit more time here for your Thanksgiving. So what are you going to spend your extra 15 minutes of your life doing? Eating turkey? You tired of turkey already?
Yeah.
Oh, why? The sales at Foodland got too much for you?
No, we just have a lot of turkey. Turkey bacon, turkey sandwich.
Already? Okay. Oh, I see. I love this time of year. I like the cheap turkeys. Of course, I've only eaten one this month so far.
What's the point of the president pardoning the turkey?
It's just a stupid tradition. I mean, it's just because we eat them, and it also I think that turkey was then used in parades. So it's a way to because the end of Thanksgiving is traditionally the holiday, the Christmas buying season. So it's kind of an economic thing. So it's just been a stupid tradition that's in part to promote capitalism. Yeah. And Thanksgiving wasn't a holiday until in the Civil War. Abraham Lincoln made it one in the Civil War. So I don't know the history of that though. I remember I just read an article about it too. Do you guys ever look at the website called The Chive?
The chive?
You never heard of The Chive? Okay, I gotta. If we're gonna talk about this, I'm gonna stop the thing because. All right.